Okay, so here's the first question for our multiple choice practice. We got a function right here. It's a piecewise function. It tells you that if a number x that you plug into here, if it doesn't equal 3, then you're supposed to plug in this top one. If it does equal 3, then it just, your y value is 6. So we got to check out each of these statements. All right, that's what these questions do. You got to see if each of them are true, and then you got to pick which of these are true. So the first one says the limit of f of x does not exist as we go to 3. So what we have to think about here is as we approach 3 from the left, as we approach 3 from the right, are we approaching the same y value? All right, so I'm going to get rid of this guy right here so we have a little bit more space. Let's get a little visual going on. As we approach 3 from the left and from the right, what's our function doing? This particular piecewise function, like if we were to plug in 3 to x, it only gives us 1 point. So it would be at 6. There's a solid point right there. But I don't know what this function is doing. And so I'm going to take the limit of just that function as I approach 3. So this is what it would look like. The limit as we approach 3 of x squared minus 9 over x minus 3. Now whenever you have just a basic limit like this, the first thing you want to do is just plug in the number. Direct substitution. If I plug in 3, do we get something? And so if I plug in 3 to the top, it looks like we would get a 9, and then we would be minusing 9, so that would be 0 on top. If I plug 3 in the bottom, it would be subtracting 3, so then we get a 0 on the bottom. 0 over 0 is indeterminate. So that means we have to do something. We have to manipulate this in some way. And since this is it's just a polynomial divided by a polynomial, we're going to see if we can factor and cancel something out. There's a difference of squares on top, and so we can factor that to be x plus 3 and x minus 3. And then really quickly, hopefully you can see, we can cancel out these x minus 3's. And so really, this is the same as saying, what is the limit of x plus 3 as x approaches 3? So let's try that direct substitution again. We take the 3, we plug it in, what do you get?
6.
We get 6. Oh, that's good news. You know why? Because I don't know what this function, this part right here, is doing on the left side. I could by plugging in a bunch of things, but I know that we're going to approach 6 from the left side, and then we're going to approach 6 from the right side. And you know what's really neat? After you cancel these out, this is actually what the function looks like, x plus 3. It's a very, it's linear. It's a linear function, so I just drew the straight lines. So let's remember that whenever it says the limit as x approaches 3, and it doesn't have like a little plus sign or a little minus sign right up there in like the exponent spot for the 3, that means this question is saying, and so we're looking at the function, and as we go to the left and as we come from the right, what are we approaching? Now because we did all this fancy stuff with algebra, we don't have to think about it like that. We just have to answer this question now. Does the limit not exist? No, actually it exists. We just found that out, so that one's wrong. This says, is f continuous at x equals 3? And the answer is yes, because that hole is filled in. Yeah. Now normally, if I were to just graph this, there would be a hole right here. And our hope is that this number right here is going to fill that hole. And it does. At 3, we equal 6. And so that hole is filled. So this one works out. So far, number 2 is correct. The last one says, the line x equals 3 is a vertical asymptote. Do we have a vertical asymptote with this?
No.
I mean, that's natural. That's what you would think, right? Because 3 would make this undefined on the bottom because we can't divide by 0. But because we can factor and simplify, this function actually looks like a straight line with a hole right here. It still is undefined at x equals 3, but there's not an asymptote there. So the last one is not true. So the only thing that's true is number 2, so your answer would be B. All right, so you asked a good question. You said, how do you know that there's not an asymptote? Because we're so used to seeing this and going, oh yeah, there's an asymptote at 3. Well, if you can factor and cross things out so that there's no more denominator, then you know that there's no asymptote. So this question is kind of mean. There's not like an exact way to figure this one out. And actually, if you plugged in, okay, well, let me plug in infinity, all right? If we plug in infinity, what's happening? All right, so you can't really plug in infinity, but you can think about what numbers you're getting as you're plugging in bigger and bigger numbers. As I plug in infinity at the top, what is sine going towards? Like, if you just think about that, like if you're looking at the sine function and it's doing its thing, right, and you're going to infinity on the x-axis, what is this telling you? What's it doing? Just going up and down, up and down, up and down. Okay, that is a does not exist limit, because it just keeps oscillating up and down. And then what's happening when this number right here is getting bigger and bigger and bigger? If we just ignore the sign for a second, what if we had a number on the bottom that was getting bigger and bigger and bigger? What is this approaching?
Zero.
It's approaching 0. You're right, because that number, that fraction, is getting smaller and smaller and smaller.
Yeah.
So actually, does what's on top really matter?
No.
No, it doesn't. So whatever is up there, it doesn't matter. The bottom is increasing infinitely, and so then you know that this number as a whole is approaching 0. So your answer is 0. Another way to think about this, which is how I thought about it right away, is the graph of sine x over x. This is a popular graph because they like to teach this to show you guys the squeeze theorem. Okay, if you look at the value right in the middle, we get undefined. You guys see that?
Yeah.
It's undefined right in the middle. That's why they like to use this to teach the squeeze theorem. But look at the graph as we're zooming out. What's happening to these x values, to this line? It's looking straighter and straighter, right?
Yeah.
It's not as wavy. And so you can see graphically that this line just starts forming to y equals 0. So that's how you know that the limit of this would equal 0. All right, so now with number 3, the first thing we do always is direct substitution. So I'm going to directly substitute into 25 to see what I get. And so I go 25, and I square root that minus 5 on top. Then I have 25 minus 25 on bottom. On the top, this simplifies to 5 minus 5, so I get 0. On the bottom, I get 0. 0, 0, indeterminate. So that means I got to see if I can manipulate this in some way. If there's a square root, then that means we're going to use a conjugate. A conjugate just means you're going to change the sign on this guy or this guy. It doesn't matter which one you choose, but we normally choose whatever's in the middle. That's what we're used to seeing. So I'm going to do that. So I'm going to take the square root of h minus 5, and then on the bottom I have h minus 25. Does it say?
Yeah,
Oh, it's minus. Okay, yeah. So my conjugate for the top is going to be square root of h plus 5. And whatever your conjugate is, it's always going to be the numerator or the denominator that has the square root. Okay, now I'm going to multiply the top, but I'm going to leave the bottom because I'm used to seeing these. I know it's going to happen.
Mr. Patey?
Yeah.
So the square root was on over minus 5.
That was a good question. Sorry, this is a side thing. But if this square root was over the whole thing, you wouldn't have to do like a plus, like the opposite sign thing. All right, you would just multiply the top and the bottom by the square root of h minus 5, like the same thing. Okay, but because the minus 5 is not inside the square root, we want to do the conjugate, what's known as the conjugate. Okay, so if you're used to multiplying binomials, you notice that these are the same except for this sign, and these are the same except for this sign, and that will give you a difference of squares. So all you have to do is you have to square the first term, which would be h squared, or square root of h times the square root of h is just h, and then you square the second term, so you say minus, and then you got 25. So on the numerator, I have h minus 25, and on the bottom, I have h minus 25 times the conjugate, which is the square root of h plus 5. I want to make sure I know that that square root only has the h inside. And you guys can see what we can cancel out. We can cancel out the h minus 25. And so on the top, you have a 1, and the bottom, you have the square root of h plus 5. So that's what we're going to take the limit of now. So let's take the limit as as h approaches 25.
So 1 over 2.
Yeah. Okay, so now I plug the 25 in. What do we get? We get 1 over, and we have 25, the square root of 25 plus 5. Okay, and that gives me 5. 5 plus 5 is 10, so we get 1 over 10. That's our answer. Direct substitution will work most of the time. Sometimes if it doesn't work, then you just have to manipulate it. So just think of manipulation every time you get an indeterminate form. All right, check out this next one. Using the table of values of f of x, the average rate of change of f on the interval blah 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 is, okay, let's decode this really quick, because that's the biggest problem whenever we come to questions like this. What the heck is it saying?
So using the brackets, I like x and y values, and I always get confused.
Yeah, right? Okay, so first thing we have to acknowledge is it says table of values, because that's pretty mathy right there. That's pretty obvious. Like, okay, so it's referring to this table right here. All right, no problem. The next thing it says is average rate of change. Now, rate of change should pop out at you like crazy. Whenever you see rate of change, this means slope. There's two different types of rate of changes that we see in calculus. There's the average rate of change and there's the instantaneous rate of change. If this did not say average rate of change, then you're just going to assume that it's instantaneous rate of change, which I hate. I hate that they do that. If the question just says, what is the rate of change? It's talking about the instantaneous rate of change. Okay, so what's the difference? Average rate of change, if you have a curve like this, average rate of change takes 2 points and you connect a line, and this is known as a secant line. The slope of this is known as the average rate of change. Okay?
This is y2 minus y1 or x2 minus?
Well, to find the slope, you just have to go y's, subtract the y's on top, subtract the x's on the bottom. But you got to make sure you stay in order. So like this is A, this is B. This first one right here would be f of A, and then this second y value would be f of B. And that's what you would have to do to find the slope. You would take f of B, subtract f of A, and then go B minus A on the bottom. This equals your average rate of change. ROC. No, whatever. So let's go back to instantaneous rate of change really quick before we finish solving this. Instantaneous rate of change is the rate of change at a point. So like if this was my point, that would be your instantaneous rate of change. It would be the slope of a tangent line. Okay, that tangent line only touches the curve at one spot. That is known as an instantaneous rate of change. That's kind of hard to find the slope if you're just using points and trying to do it like this, because you only have 1 point right here. You can't subtract 2 y's on top and 2 x's on bottom to find this slope. So there's other things that we can do. In this unit, because we're doing limits, you can only do it like numerically or with a graph. Like if I had this graph, I could just count the rise and run, and that's going to be my instantaneous rate of change. Numerically, you would plug in a bunch of numbers and find a bunch of different slopes, which maybe we'll encounter in a little bit, and that's how you would estimate the instantaneous rate of change. But later when we do derivatives, we'll find the exact instantaneous rate of change. So,
is answer 1 or no?
We'll get to that. Okay, so the average rate of change. So I just did all this to explain that word, okay, of f on the interval. Now what is this? What are these numbers right there?
X's.
Yes, these are x's. X values.
Yeah.
Okay. Dork. So this interval right here, -2 to 4, that's kind of like saying your a is -2 and your b is 4, and you got to find your slope. So let's do that right now. They kind of give us everything that we need in our table. So we have a -2, and what's the y value for that one? 1, and we're given is that 4? Yeah, 4 is 15. So all we gotta do is 15 minus 1 on top, and then 4 minus -2 on bottom. If you change the order, it's fine. You'll get the same answer. We have 14, and then over 6. That's gonna be 7 over 3. And so that's D. Okay, let's read this next one. This one's kind of confusing at first. Okay, so when I'm reading this, I see, suppose that the limit as x approaches 2 of f is 5. As we approach 2 for g, it's 6. And then we know this stuff. Now, this looks like sandwich theorem stuff, or sandwich theorem or squeeze theorem, because it's telling us that f is less than h, and g is greater than h for all x. So I'm thinking like, man, are we going to be doing the squeeze theorem here? And then it says, which of the following must be true? Okay, so this is just information. Now we have to see if any of these are true. So what does this stuff mean? Okay, do you know what limit means? Do you know what this stuff over here might mean? Okay, so this says if we plug 2 into f, we would get 5. Now, what do we know about f? We know that the limit as we approach 2 is 5.
Yeah.
Does that mean when we plug in 2, we get 5? No. And so what I'm thinking of is a counterexample, something that looks like this. Now, I don't know what f looks like, but I do know this, that when we're approaching 2 from the left and then from the right, I know that, yeah, we're going to approach 5. So, like, let's say this is 5. We're going to go up to 5, and then we're going to go away from 5. Because on both sides, the left side and the right side, we're both approaching 5.
So
now, could we have a solid dot there?
Yes.
Yes, that's possible. But could we have an open dot there?
Yeah.
Yes, that's also possible. So, we don't know this. If this is true, then we know that there's a solid dot there. But we don't know if we have a solid dot there. It could be an open dot. So this one is not true. I'm going to put an X next to that so I don't forget. Next one says that G is less than or equal to 6. Is G less than or equal to 6 for all values of X that are greater than or equal to 2? Okay, so that's it for Roman numeral number 2. We can't decide this. Actually, like, the fact that f is less than 6 or g is less than 6, we don't know that for sure. We do know that g is greater than h and greater than f. We know that the limit at 2, we get to 5 on f, and the limit at 2, we get to 6 on g, but we don't know if all the values of g are less than 6 based on what we're given right here. Now, this one is the trickiest of all of them, number 3. We would almost say that this one's true, because this actually looks like the squeeze theorem. It's saying that the limit of h, which is always greater than f and always less than h or g, is between these. We don't know that. We don't know that for sure. Now, the squeeze theorem says that if the limit of the lower function, which is f, and the limit of the upper function, which is g, if they equal each other, then we know what the limit of the middle function is. But they don't equal each other. One is 5 and one is 6. The limit could just not exist. There's one contradiction right there. Let's say the limits for, like, let's say g looks like this, right? And then f, that's the upper function, then f looks like this. It says that the limit for f is at 5. The limit for g is at 6. Now, in comes the middle function. It stops right there, and then it stops right there. There's a jump discontinuity right there. There is no limit that exists for the middle function, which is h. All right, we don't know, so we can't say this. We can't say that the limit's going to be greater than 5 and the limit is less than 6. It is so close to being the squeeze theorem, it would fool a lot of people. This one is E. To clarify, the squeeze theorem says that if you have a function and you don't know what's happening with the function at some point, let's say it's undefined right there. Okay, we don't know what's happening right there. But then you know that the upper function is always above it and the lower function is always below it. If they all equal the same limit, if they all equal the same thing, then we know for a fact that the limit of the middle function would be the same as the other two. So if these two limits were the same, if they were all going to 6, then we know that the limit as we approach 2 of h would also be 6. That's what the squeeze theorem says. Now let's do the next problem. Okay, this next one is talking about the intermediate value theorem. If f is continuous, that means no holes, no jumps, okay, from 2 to 6. So I want to kind of draw us a little visual to help us out. So from 2 to 6, this says that we're continuous. So let's just draw something continuous. Whatever, doesn't matter. So straight line, no holes, no jumps. Oh wait, it gives us values for 2 and 6. So let me make this a little more exact. So 2 is up here at 20, and then 6 is down here at 10. Okay, and these are connected somehow. Okay, all right, no holes, no gaps. Okay, so we know that at 2 we have 20 and at 6 we have 10. All I'm doing right now is I'm translating this because I want to understand what it's asking. It says, then the intermediate value theorem says, okay, that's IVT. Some of you guys remember it just by the initials. The intermediate value theorem says which of the following is true. Now, before we read these, the intermediate value theorem says that between 2 and 6, we're going to hit, let's say 16. You have to. You have to hit 16 at some point on that line. You can't not hit 16. You are also going to hit at some point 11.1. Like, so all those numbers between 10 and 20, you're going to hit those somewhere. So I can call it any number I want. I can say, where does y equal 10.5? And we know that there's a value c that if I plug into my function, I'm going to get a 10.5. Why? Because this is continuous. I'm going to hit 10.5 somewhere. It looks like we hit 10.5 right here, so maybe the value c would be really close to 6. All right, that's what IVT says. Now let's read our statements. F of x equals 25 does not have a solution on 2 to 6. Do we know that? Do we know because of IVT that f of x equals 25 does not have the solution? So that's saying this. Is there a c that equals 25? Does that exist?
No.
Okay, we don't know that. IVT doesn't say anything about 25 because 25 is not between 10 and 20, right? So I'm going to put a little X next to that dude. We don't know.
So we take off A and...
All right, Denrick, I gotta bring this up because that's a good point. You're already looking at the answers trying to eliminate things. I wouldn't do that. I always look at all the statements first and decide if they're true or false, then look at this. Then if you find a contradiction, you can go back and see if you messed up somewhere. But I would not go at the answers because the answers are sometimes made to mess you up. They're looking for answer seekers and trying to throw you off. So let's look at the next one. This one says f of x equals 17 has a solution.
Yep.
Okay, is that true?
Yeah.
If I change this to 17, can we say that is true? Yes, because between 10 and 20, we got to hit 17 because 17 is in between those. So that one's true. Let's look at our last one. Our last one says f of x equals 0 has a solution on from 2 to 6. So is there a c that will give you 0?
Nope.
Yeah, we don't know that.
Yeah.
Now, could that be true?
Sure.
Could it be true? Yeah, it could, but we don't know for sure. See, look, I can redraw this function. I can say, this function will start at 20, end at 10, but this function actually goes like this. Okay, in this case, look, f of x equals 0 there, f of x equals 0 there. So it could be true, but do we know for sure definitively because of IVT? And the answer is no, we don't. So this is a no, so our answer is only 2. Okay, so just a side note, make sure you know that f has to be continuous on the interval for IVT to work in that interval, okay? And then, I don't know, checking answers as you're looking for the answer, as you're solving things, isn't always a bad idea, but it's normally like a last resort. Like, let's say you don't know the answer, you don't know if number 3 is true, then you would start eliminating, because then you would have a 50% chance to guess it right. I think I see what you said. Because you said, like, 1 is not true, so that means this one doesn't work, this one doesn't work, and this one doesn't work.
Because it all has 1.
And so, like, if you find out that 2 is true, then this one can't be it. Okay, but here's the thing. What if you looked at 3 and you know for sure it's true?
Yeah, but...
Then you got to go back and you got to check 1 again. Because what if you did 1 wrong? See what I'm saying?
Yeah.
That's why you never want to, like,
unless you're
play the game.
positive, 101%.
Right.
Sure.
You got to be 101%. But I can't tell you how many times on a test I was 100% sure that something is wrong, and I kept reading and I figured it out, and I was like, holy crap, that other one, I must have done something wrong. I was like, oh, dang, I forgot a
great
negative.
example was the quiz we took. Everyone thought the first and second was right.
Yep, and then they skipped.
They skipped the third one.
No,
but it
but
was
even
actually
then, it wouldn't have